In this video, we're going to discuss how polynomial transformations can be used to estimate nonlinear relationships using linear regression techniques. But before we do that, it's helpful if we define two concepts or two different definitions of a linear relationship. We say that an equation is linear in variables if the dependent variable can be written as a linear combination of the independent variables, in this case x1 through xk. That's the way in which you've normally seen linear relationships. However, what we really need in order to be able to use regression techniques is something a little bit weaker than that. The relationship that we really need is that a function be linear in parameters. And when we say that it's linear in parameters, what we mean is that the dependent variable can be written as a linear combination of functions of the underlying variables. And those functions can take any form. The underlying principle is that if we can express something in a form that's linear in parameters, we can use linear regression techniques by just replacing the functions in there, f1 through fk, with new variables, z1 through zk, where z1 is equal to the first function of the independent variables, z2 is equal to the second, and so forth out through zk is a kth function of x1 through xk. Basically, we can use linear regression techniques to estimate the model if we can find functions, f1 through fk, that will allow us to express a relationship in the form that's linear in parameters. And then once we have it in that form, by defining these new variables, we now have a relationship which is linear in these transformed variables. This transformed relationship is linear in the newly defined variables z1 through zk. And once we have it in this form, we can now run a regression of the dependent variables on these transformed variables. The easiest way to see how this works is to take an example. And one of the simplest and most commonly used examples of this type of transformation is to estimate polynomial relationships. So we're going to examine some polynomial transformations. And a polynomial can be written in the form y is equal to beta 0 plus beta 1x plus beta 1x squared out through beta k x to the kth power. There's a theorem in mathematics called Taylor's theorem, which tells us that any continuous relationship can be approximated to any desired level of accuracy by simply choosing a polynomial of sufficiently high order. So by choosing a value of k that's large enough, we're going to be able to approximate any continuous function. The basic principle of the polynomial transformation is that we use zi equal to x to the I. So all we need to do is replace each of those powers of x with a new variable z that's defined to be that power of x. While the original relationship is a nonlinear function between y and a single variable x, this transformed relationship is a linear function of these transformed variables. In particular, this new function is linear in the variables z1 through zk. So all you need to do to estimate a kth order polynomial is you let z1 be equal to the original variable x, z2 is equal to the square of that variable, z3 is equal to the cube of that variable, and so forth out to x to the k. So you define zk equal to x raised to the kth power. In practice, though, the most common forms of polynomials that are used are linear models, which we've already seen, quadratic models, which are used very often in econometrics, and occasionally cubic models. It's very rare that you will need a polynomial of order greater than 3 to approximate most of the relationships that we see in applied econometrics. Linear models are pretty straightforward. They're either downward sloping or upward sloping, depending on the value of beta 1, as we've talked about before. If we have a relationship that appears to be linear between y and x, then a linear model is appropriate. However, we will often see relationships in economics that look something like this, and we'll talk about some examples in a moment. And these are quadratic relationships. And on the screen, you see the signs of beta 0, beta 1, and beta 2 that are needed to get this type of shape. But if you think back to your introductory microeconomics or macroeconomics classes, you may remember seeing curves that look like this in a number of applications. And those are among the applications where you'd use this type of relationship. A cubic relationship is often some type of an S-shaped curve like this, or an inverted S-shaped curve. And again, the signs and the magnitudes of the coefficients that would give you these specific shapes are listed on the screen. If we just consider the relationships you've seen in your principles of economics courses, most of them would tend to be represented or approximated very well by either linear, quadratic, or cubic models. Specifically, some common applications of these models that you may be familiar with from prior economics courses are, in the case of a quadratic model, this is often used to represent age earnings or experience earnings profiles. What we observe is that when people first start at their jobs, their earnings tend to go up initially at a relatively rapid rate, but then the rate of increase gets smaller, and beyond some age, earnings may actually decline. And there's a lot of reasons for that that are discussed in other courses, but that sort of inverted U-shape is one that we observe quite a bit in labor economics, for example. If you think back to your principles of micro course, average total cost, average variable cost, marginal cost, average product, and marginal product curves all can be approximated by a U-shaped curve or an inverted U-shaped curve, or some portion of those curves. And the shape of total cost and total product curves that you've seen in your introductory economics courses look very much like those S-shaped or inverted S-shaped curves that we've just seen. So, including squared and cubed terms of the original variables will allow us to approximate nonlinear relationships between a dependent variable and an independent variable very nicely. This allows us to represent a much larger class of economic behavior using linear regression techniques.